Next, we compute C. For that purpose, we rewrite h of s is equal to d, which is 1 over j omega squared plus 2j omega. Let me erase this. Okay, we're gonna restart fresh. So we're going to write that h of s, which is 1 over s squared plus 2s plus 1, must be equal to c plus 1 over j omega squared plus 2j omega plus 1 times 1 over s minus j omega. Or we must have that c is equal to 1, my mistake, c must be equal to 1 over s squared plus 2s plus 1 minus 1 over j omega squared plus 2j omega plus 1 divided by s minus j omega. So it is not as much a business of derivatives that we need to compute, rather than simplifying polynomials. For that purpose, what we're going to do is we're going to eliminate all this. I mean, we have a clear picture of what it is. All right, so that was not a good drawing. But instead, we're going to write that c is equal to 1 over s minus j omega times 1 over s squared plus 2s plus 1 times 1 over j omega squared plus 2j omega plus 1 times j omega squared minus s squared plus 2j omega minus s plus 1 minus 1, which is 0. So we forget about this guy and we concentrate on this guy. It turns out that this is also equal to j omega squared, j omega minus s times j omega plus s, and there is a 2 missing here, and so this becomes plus 2 times j omega minus s. So we see that we have an s minus j omega here, we have an s minus j omega there, so we can rewrite that c will be equal to minus 1, because there is a j omega minus s here and s minus j omega there, minus 1 times j omega plus s plus 2 divided by s squared plus 2s plus 1 times j omega squared plus 2j omega plus 1. As you see, that is a function of omega, but that is the original system. And what happens is that when we take the inverse Laplace transform of C, it goes to 0. Therefore, when we take the limit when t tends towards infinity of the inverse Laplace transform of C, because up to that factor j omega, it is the inverse Laplace transform of this term, and we know that this is an oscillatory but decaying exponential. And therefore, what we get is that the limit when of t, the output of the system when t tends towards infinity, is simply the inverse Laplace transform of d times 1 over s minus omega, and therefore it will be behaving like 1 over j omega squared plus 2j omega plus 1 times e to the minus j omega t, or e to the j omega t, sorry. So in the limit, that's how it behaves. All right. And so we can rewrite this as h of j omega times e to the j omega t. Okay. And that is the steady state answer. While this term here is called the transient. Now let's do a little bit of an experiment by introducing Scilab. I introduce the variable s, and I introduce the system, so h is equal to 1 divided by s squared plus 2 times s plus 1. I write cis equals cislim of h, which allows me to, oops, I forgot to specify that it was in a continuous time domain, my mistake. And then I can plot the response of that system to a e to the j omega t. Now, so we're gonna write j, okay, so j equals square root of minus 1, okay, and we're going to, so this is I, the traditional notation, and I'm going to write t is equal to a certain interval that goes into increments of 0.1 until about 30, okay, for lack of a better idea. And we're going to write that u, okay, the input to the system is going to be equal to e, so exponential of j times, we're going to pick omega, okay, we're going to pick omega as an exciting frequency of about, I don't know, like 6 radians per second, or maybe 2 radians per second, or maybe 1 radian per second. So in that case, there'll be 1 radian per second times t. Let's see if that works. It sure does. And we're gonna write now the response of the system to that input. Okay, so we're gonna say that we're gonna call help csim. Okay, I'm going to see what csim allows me to do. Okay, so I need to specify u my input, t my time, and then my system. Okay, so we're going to say z is equal to csim of, we said, hold on, I forgot even what my u was. Okay, so z equals csim of u, t, sys. Okay, and let's hope it works. We have a problem. So let me call csim again and see what I messed up. U, t, sys, haha. I suspect that it doesn't like my input, okay, because it's u is a complex input. So I'm going to say u1 equals real of u, and u2 equals imaginary part of u. Perfect. Let's start with the input. So we're going to say z1 equal to csim u1 t. Okay, it likes it better. z2 is equal to csim u2, t, sys. Okay, now we're going to plot t, u. Okay, so that's the input. Alright, so that's a sinusoidal input. Okay. Second, we're going to plot t, z1. And what you see is that after a small transient, z1 is just a sinusoid times a regular sinusoid, okay, which is somehow lagging behind u. Okay, u reaches its maximum here, z reaches its maximum there. So that's the real component response to the real input, which is cosine of t, because again, e to the jt is equal to cosine t plus j times sine t.